I would like to welcome you all to the BIMR Seminar for this week. It's a real pleasure for me to introduce our speaker, Professor Markus Piro from the Department of Engineering and Physics. Professor Piro received his bachelor's in engineering in mechanical and materials engineering in Canadian University in 2005. He then stayed in the same department, mechanical materials engineering, for his master's degree, which he completed in 2007. And then he moved not very far. He moved to the Royal Military College of Canada, or RMC, for his PhD studies in nuclear engineering. And he completed his PhD in 2011, and then took up an NSERC postdoctoral fellowship.
Not NSERC.
Oh, it wasn't NSERC?
No.
Oh.
That doesn't matter, but yeah. Doesn't matter. Yes.
Which took up at Oak Ridge National Laboratory in Tennessee. He was there from 2011 to about 2013 before being recruited back to Canada as section head at the Canadian Nuclear Labs at Chalk River. He stayed there until 2016, and the following year moved to UIT, or Ontario Tech, in Oshawa, where he became associate professor and department chair right away.
Oh, not the chair right away, but eventually.
And eventually chair. Right away. There's the chair of the Department of Energy and Nuclear Engineering. Stayed there until 2024, when we were fortunate to recruit him to McMaster as associate professor in the Department of Engineering and Physics. He has now established himself in that department, and the research program kind of focuses on nuclear fuels and materials for advanced nuclear reactors. And today he's going to tell us about his work. The talk is entitled, "What About the Nuclear Waste?" Markus, please join me in welcoming Professor Piro.
Oh, wow. Thank you. Thank you very much for the introduction. Hopefully you guys can hear me okay. I've never been in this room before, but it's like going to a sports game, going to a hockey game. It's very steep up there. I'm not playing for the Toronto Maple Leafs, but hopefully you enjoy this talk. So it's a real pleasure to be here at the Brockhouse Institute. Pleasure to be here at McMaster. My career I spent in nuclear fuel engineering, dealing with a number of matters related generally to safety and licensing, mostly in reactor, but we also do work in other areas as well. There's a reason why I wanted to give this particular talk. It's because I've seen like a lot of things in society becoming really, really polarized, and not just politically, but kind of across the spectrum. And this is one topic that's very polarized. So what I thought I would do is give more of a technical, fact-based presentation of what the nuclear fuel is really all about. And so, I don't work for the Nuclear Waste Management Organization. I work for McMaster University. I spend my career trying to factually investigate various matters related to nuclear fuel. So I hope that gives a bit of context to why I gave this presentation. But first and foremost, I want to give thanks to the invitation. Thank you also to Florian for making the organization of it. Really appreciate it. I also want to give some respect to Bertrand Brockhouse, Canadian nuclear science pioneer. Excuse me. Did some very groundbreaking work at Chalk River National Labs, but also here at McMaster University. It's awesome. I got some students from my undergrad nuclear course who actually used some of the facilities that Brockhouse got to use when he was here. And they're doing that in their undergraduate lab. About 15 years and 15 pounds ago, that was me. That was back when I was in Oak Ridge. I know, right? I had more hair then, but I couldn't take a picture with my eyes open. Anyway, so that's me. We organized an event with ASM where we had the son of Clifford Shull. Clifford Shull shared the Nobel Prize with Bertrand Brockhouse. Really, really honored to be part of that presentation, and just want to give some honor to Mr. Brockhouse. So first question is in regards to nuclear energy here in Canada. Where are we at? As it stands now, this picture here gives a pretty good graphic of the energy distribution across Canada based on different provinces and also their energy source. As it stands today, we have here in the purple circles represent nuclear power, which is I'm focusing on today. In Ontario, that's the largest share, depending on the year, 50–60% of the electricity in Ontario is from nuclear power. New Brunswick has a nuclear generating station, but that's pretty much it right now. The federal government of Canada is projecting all the way out to 2050 as part of a net zero plan, which is shown in this graphic here. Very much different than it is today, not only in terms of the quantity of electricity that's going to be required to be put on different grids, but also where those sources are coming from. As it stands, and the major objective there is really to get towards net zero. That net zero plan includes the elimination of coal, reduce reliance on gas, wind turbines, and also nuclear power in different jurisdictions. You can see Ontario is expected to increase, as are pretty much all of other provinces to some level of degree. So there's some anticipated growth with respect to nuclear power here in Canada, and that means that we also have to be thinking about the waste that those nuclear generating stations are going to be producing. There's more arrows. Never stops. Keeps on going. So first question, what is waste? Well, there's a technical and legal definition, but basically what it comes down to is the waste. It's, you consider it waste based on who actually owns it. Think about it in your house. What I consider waste is what I put in the trash can in my house. Another person, can't say that some cup is waste if it's not their cup, not their house. So whoever owns the waste can classify that as waste. As it stands, the utilities largely own the waste here in Canada. There's 4 different classifications of waste, including low and intermediate level waste for things like medical isotopes that are produced, for the diagnosis and treatment of cancer, produces a large volume of that. Today, what I'm really focusing on is what's called high level radioactive waste. That's from what's called used nuclear fuel. This is what a can-do fuel bundle looks like. Also have one here in person. This, what I do with some of the students, maybe I do with you guys. I'll say, yeah, this thing actually has uranium in it, but you'd be surprised how often that works. This does not have uranium in it. It's an empty bundle. So this bundle is about, just pass it around. Please don't drop it. I use that for teaching purposes. So it's not so much me that loses, it's the future students that would lose. Please don't drop it. So yeah, anyways, so a real bundle would be about 24 kilograms, about 50 pounds, 53 pounds. It's about ½ a meter long and, or about 19 inches or so. One of those fuel bundles, the metal that you see encased is made out of zircaloy 4. That's a type of zirconium alloy that works pretty well in a reactor. Inside of it, you'd have these, what are called fuel pellets. This is just a little plastic one, but it's kind of close to the dimensions. Maybe I'll do it this way. Sorry, I missed out here. Don't worry, we're going to get to lots of chemistry. I know you're interested about chemistry. So inside of that bundle, there'll be a stack of fuel pellets. The fuel pellets are made of uranium dioxide, and that's what makes a lot of the fuel. One of the important things to note, the energy density is very high. So one of those fuel bundles that's being passed around now would produce the amount of electricity for the average Canadian home for over 100 years. So energy density is pretty high. What that also means is that if the energy density is pretty high, it means that the volume density is also pretty high. So what's also worth noting is that one of those bundles gets abused pretty badly when it goes inside of a reactor. What I mean by that is, also I could pass these around. This is like a model pellet, just made a lot bigger so that you can feel the dimensions in your fingers. So this is quite a bit larger than a real pellet. The plastic one that was passed around is close to the actual size. This one is a little more geometrically accurate in terms of shape. Yeah, so the bundle gets a lot of abuse in reactor. Can go from about 270 to about 310 C. Pressure, 10, 11 megapascals. It's bombarded by radiation. It's a slightly corrosive environment. And so it's getting pretty beaten up when it's inside of the reactor. The bundles are designed so that they can withstand that pretty nasty environment within the core. It's a bit of an important point to make because the harshest environment that it's going to experience will be inside the reactor. Inside, like I said, you got these fuel pellets. They look like these. The way that they're manufactured is it's a multi-stage process through the fuel cycle, but eventually you end up getting uranium dioxide powder. It's pressed, through mechanical means, a mechanical press, and then it goes through a sintering process, and then what results is the very hard ceramic. There's a few reasons for that, one of which is that very hard ceramic is very good at retaining all this nasty stuff that ends up produced inside of it in core, and we'll get to that in a second. So, wait, we're gonna do a little survey. How many people here are materials, like from the materials department? Okay, Eng Phys, bunch. Other engineering? Outside of engineering? Wow. Okay, so outside of engineering, where are you guys coming from? Science? Okay, what else? Wow, what a mix. Anyone like business or social science or anything like that? One? Okay, yes, sir. Interesting, cool. Okay, so nuclear physics on one slide. Here we go. Here we got a uranium-235 nuclide. My students that took my nuclear intro course, well, you guys can give the lecture here, right? Anyways, so the main thing to understand with fission is that only some nuclides can actually undergo fission, uranium-235 being the principal one. So what ends up happening here is you bombard it with some neutrons, and that uranium-235 can become unstable and then split apart. So here we got our neutron, splits in two, thanks to my fancy graphics from my friend Dan. And so that fissile nucleus was once a heavy uranium-235 nuclide, and it split apart into two lighter nuclides with 2 or 3 other neutrons. The important part for today's talk is that you once had a really heavy nuclide, now you have 2 of something else. So what's that something else? This figure here shows what that something else is on a statistical level. You have a distribution of radionuclides, kind of shown, represented by this. Might not make a whole lot of sense, but the point is that you get a spectrum that covers pretty much the whole periodic table. And that spectrum varies in concentrations. What does that look like in practice? It's represented here on this plot for typical can-do fuel. This plot is basically showing you, without getting into the jargon mumbo-jumbo, burn up is basically how much energy has been burned by burning up that fuel bundle on the back, meaning like at the back end of it, this is roughly what comes out of the reactor. The vertical plot on this thing shows different fractions of different elements that are coming out of that fuel bundle, well, like within the fuel. So I don't know if you can see it too well. I'll just read out a few of them. This is in addition to uranium dioxide. So we got plutonium, xenon, zirconium, molybdenum, ruthenium, Pretty much the entire periodic table is now produced within this uranium dioxide fuel pellet. So that's a lot. What's worth noting is that you have now the entire periodic table in like a single pellet form. It's very important to understand how does that perform on a materials and chemical kind of perspective. You guys materials people, I'm sure you love crystallography. Everyone loves some good old crystallography. Here we got this fluoride crystal structure, which represents uranium dioxide. I'm going to give Material Science 101 right now because we have a pretty diverse audience. What you're basically looking at here is the arrangement of atoms within this uranium dioxide material. The red atoms here, the red circles represent oxygen, the black one's uranium. Why is this important? Is that if you look at this, you might notice every other cube here will have a uranium atom, the other one is empty. Why is that important? Well, when that uranium atom splits, I go from 1 to 2. So if I had a spot for 1, where's the other one going to go? Well, I got a friend right next door, a next little cube right next to it, where that other atom, the other fission product can go. That's an important feature of this particular material that's chosen for nuclear fuel. So those fission products that are formed, again, talking about the whole periodic table, you get different classes of fission products based on their chemistry. Like how do they volatilize, right? If you think about the entire periodic table, they're broken up into different regions based on their chemical behaviors. For the fuel, it's typically broken down into these 4 categories: the gas and volatiles. You got semi-volatiles, low volatiles, and non-volatiles. So what that basically means is like, how easy is it going to come off? How do we understand this? Well, over decades of work, typically at various national labs around the world, you'll use, let's say, research reactors to irradiate some of these fuels, and then you'll characterize them, for example, in these hot cell facilities. We have both a reactor here and hot cell facilities here at McMaster, although we're not doing fuel irradiations for testing purposes, but it gives you a bit of an idea of what can be happening. So through that experience of irradiating different types of fuels, we got a better understanding of how does that materials and chemistry behave of those fission products. What generally happens is that we typically get 3 different phases forming the fuels. There's the original fluoride crystal structure. We got gas. We have gas bubbles that are forming. You got to think about those gases. And then a 3rd phase, which are some noble metals. And you can see them right here, these little guys here. They're often called the white phase. Try to keep things simple in nuclear. Instead of giving it a fancy, crazy name, we just call it the white phase because it looks white under like SEM, scanning electron microscopy. So the main concern with these fission products, the main concern with this irradiated fuel is really the radioactivity of the fuel itself. You have radiation that's coming off, and you want to be able to understand that. You want to be able to predict it. You want to be able to control it. And you want to be able to monitor it. So for those who are not familiar with radiation, there's several different types of radiation. In this context, the 3 we really want to be thinking about, at least for used nuclear fuel: alpha particles, beta particles, and gammas. So alphas, a great example of alphas, if you ever see your smoke detector in your house, it usually relies on alpha radiation. Betas, if you ever eat a banana, bananas contain potassium-40, natural beta emitter. Gammas are a form of electromagnetic radiation, like light, just a different frequency. So these are very different types of radiation, but you can also shield them in different ways. So for example, alphas can be blocked by just a sheet of paper. They can be damaging, but it doesn't take a whole lot to block them. Beta particles, you can give it thin aluminum foil, like that you might wrap up some of your food. Some aluminum foil is enough to block these betas. Gammas, you need a lot more. So with gammas, you typically need like concrete or lead shielding. So hopefully you've all gone to the dentist. You've had your dental x-rays. Even though they're x-rays, not too different than gammas. You always put on lead shielding, right? A lead blanket. So same idea here. Whoop. You can block some of those gammas from having some lead. Okay, so what does the radioactivity actually look like for the spent fuel? Here's some plots of projections. This is for candy fuel. I want to break it down a bit here, and because there's a lot going on. And you might also see some of this in some of the literature, but I want to give a little context. So on this is a log-log plot. The horizontal axis is time in years. The vertical axis is radioactivity. I want to just point out that the horizontal axis starts at 10 years. So that's after 10 years of it coming out of the reactor. And an important thing is you'll note, log-log plot, this is exponentially decaying. That's a natural process, just like gravity. So the radioactivity is decaying. What are all these different colors representing? Well, the black color, on the top, represents the total radioactivity of that spent fuel. Then the different colors below it correspond to the different contributors to that radioactivity, broken down by like the fission products, which is shown in this red. So you can see that the fission products are dominating the total reactivity in the short term for the first few hundred years. In the longer term, the radioactivity is dominated by this blue curve, which are the actinides, so uranium and plutonium, for example. So you can see how that changes. One of the other reasons why this is important to think about is that the chemical form of those fission products, we talked about that a few slides ago. You have different categories. You have gases and volatiles, for example. Those guys are largely the fission products that you're thinking about in the first few hundred years. Whereas the non-volatiles, your actinides, are really on the back end. So that means from a chemical perspective, the ones that are least volatile are the ones in the longer term. The ones that are most volatile are in the short term. Now, in addition to radioactively decaying, they also generate heat. The amount of heat that is generated from this radioactivity also goes down exponentially. It's roughly proportional to the amount of radioactivity of the fuel. You can see that by this plot here. And in this one, this is a different scale, more so in the context of like years coming out of the reactor. But what I just want to highlight here, see if this laser pointer works. You can't even see it, it's such a big class. That's okay. So what I want to point out though is that roughly about here, this is where the used nuclear fuel will come out of what's called wet storage, and I'll talk about that in the next slide. So you can see that the amount of heat that is given off by this spent fuel goes down quite a bit. So what does that mean practically? It's about 1,000 times lower in terms of the heat load from after it comes out of the reactor to the point where you're transitioning from wet to dry storage. So you got to be thinking about this heat load. Now, what do I mean by this wet storage? When the fuel comes out of the reactor, it's very radioactive. It's very radioactive. It's also generating a lot of decay heat. You can't just take that and put it on the table here, right? Or on the floor, if you will. What needs to happen is you put it into what's called wet storage. So these fuel bundles, incredibly radioactive, you put it into a large pool. Now, it's not a swimming pool, but it'd probably be the largest swimming pool you've ever seen in your life. So in these pools, the reason why you do that is that the water provides excellent shielding. So if you remember a few slides ago, I said, we got these different types of radiation, got to think about gammas. Water is great at shielding gammas. Also, it provides a really good heat sink for the fuel. So it's generating a lot of heat, right? Decay heat, surrounded by water, you got a heat sink. So what happens in these stations, after it comes out of the reactor, they're going to put into wet storage for about 7 to 10 years. Now, so how do we know that's really good shielding? Well, you guys are all, or most of you are scientists, engineers. We do something called a measurement. This thing is a gamma gun, well, colloquially, or called a survey meter. Thank you very much, McMaster Health Physics, for letting me borrow this. So this is an example of an instrument you'd use to measure gamma radiation. So this gamma gun looks very similar to the one on the screen. I think it's actually the exact same model, which works out beautifully. So this thing is used by what are called health physicists. Also are there a bunch of undergrads in the class? I know you guys are. So if you're looking for jobs, there are gonna be tons of jobs looking at health physics, where you make sure that, from a radiation safety, these nuclear facilities are safe. So the picture you're seeing here is of the Bruce Nuclear Generating Station's spent fuel pool. You can see a YouTube video of this. And what is happening here is the giant pool of water provides shielding and cooling for the spent fuel bundles with a significant amount of water head from the top of the bundles to the surface of the water. And it's a little bit blurry, but it says 0.0, well, in this case, millirems per hour. So it's not registering any radiation off the top of that. After about 7-10 years of the spent fuel going into wet storage, then it goes into dry storage. At this point, you remember that curve, the radioactivity's gone down quite a bit. It's still generating some heat, but it's much more manageable heat. So what happens here is that these large casks, it's about 60 tons, will be put inside of the spent fuel bay through a crane. And then what they'll do is they'll start loading in trays of these fuel bundles to each one of these casks. Once that's full, then you use a giant crane to pull the whole thing out of the water and then bring it down. Once it dries off, this is again within the station, a lid is put on, welded shut, and there's an IEA, International Atomic Energy Agency, mechanism to secure that. So this picture here shows, again, with your gamma gun, the amount of gamma radiation that is then measured on the back end of this cask. More specifically, it's a little hard to see it from this picture, but if you see the video, it makes a little bit more sense. On the bottom end of this cask, you have a drain pipe. It's intentionally not a straight drain pipe. And the reason why is because if you had a straight drain pipe, the radiation can go, just like light, goes in straight lines, right? So then that radiation would go straight outwards, but it doesn't. You have corners and bends that goes around. And this picture here shows the measurement of 0.1 milligram per hour, practically nothing. Just for reference, public areas, the limit for public areas that do not even require posting is 2. So you're over an order of magnitude less than that. So it's nothing coming out of that. Okay, so now let's take a look at where the spent fuel is located. There's several locations here in Canada that are located on this map. There's some in Whiteshell Labs, owned by Atomic Energy of Canada Limited, as is up here in Chalk River. Those are in big national labs. So if you guys are looking for jobs and research, that's a place to look at. And then there's several other the utilities, Bruce Nuclear Generating Station, Pickering and Darlington Nuclear Generating Stations, also in Ontario and New Brunswick. We have the Point Lepreau Station and McMaster shown over here. See, we're famous. So we got spent fuel that's located here at McMaster. It's located currently in the McMaster nuclear reactor. We have records and projections, so records to date of where we are at with respect to the current inventories, and then every year there's an update on the projections of where the existing operating stations, what inventory they will generate to the end of their license of their applications. So there's a lot of numbers here. You don't really need to know all of that, but the more important thing is that where we're currently at is about 3 million of these fuel bundles. And with current projections of existing operating station, the projection is about 5.4 million bundles. So that might seem like an awful lot of fuel bundles, but what I think is important to remember is that the energy density is very high, which would mean that, if you were to convert that, let's say, or generate that same amount of electricity through other means, then the volume and mass of that waste could be significantly higher. Oh yeah, as shown here. So a single pellet, so like that little plastic one that was in the back of that cardboard thing, an actual pellet would be about 20 grams. There it is right there, which would be the equivalent to less than half a ton of coal or 410 liters, what is that, oil. That's an awful lot. So if you burn, let's say, 400 kilograms of coal, that means you're going to have of the order of 400 kilograms of waste, except in that case, it's in the form of greenhouse gases. So the main difference here is that you have very nasty waste, but it's incredibly dense and concentrated. Here in Canada, the plan is to have what's called a Deep Geological Repository, or DGR. This is managed by the Nuclear Waste Management Organization. They're using what's called an adaptive phase management approach in order to approach final disposal of spent fuel. The basic idea here is we'll have an underground geological repository. So just before Christmas, the site was located. I'll get into that site a little bit later. The basic idea here is you take all of that waste and you bury it underground about, look like they're leaning towards about 750 meters underground, and using a multi-buried approach, which I'll describe in the following slides. To put things in perspective, 750 meters, the CN Tower is about 550 meters. So it's about 1.5 CN Towers in terms of the height. And so in order for this to actually proceed, to be clear, the way things work in Canada is a company can't just go do something. We have a nuclear regulator, the Canadian Nuclear Safety Commission, and a licensing process in order to do these things. For example, here at McMaster, if we wanted to do any work like at a nuclear facility, we have to have a license here at McMaster to do that. So we have a reactor here that is used for doing things like medical isotope production for cancer treatment. We have neutron radiography for non-destructive examination of commercial airline turbine blades. We need a license to do that. The way that the license works here in Canada is you have 3 major stages. The first one's a license to prepare site. So what that means is pick a site, do an environmental assessment of that site, and make sure that everyone's good. The second one is a license to construct. That means that, yeah, you got a site, now you have to apply for actually building the thing. You can build it, but it doesn't mean that you can run it. That's the third stage, license to operate. So the license to operate application says, here's the final major hurdle for us to actually run the thing. The way that this works is that the regulator puts out notices way in advance. Here we're gonna have this license hearing, and the general public, you can participate in this. You can also do what's called an intervention. So for example, if you wanna have a public statement of your views, either as an individual or as an organization of whatever that license is, you could put it into the formal record. You can have a letter, and or you can go in person to see it. We had this end just recently for OPG's other license for the Darlington New Nuclear Project, ended this Tuesday. You can click on that link. We're gonna make the slides available after the thing if you wanna see us. And you can even see all the videos and things like that for that last one, just to give you an idea of what would be required. The basic timeline that the Nuclear Waste Management Organization plans for this project is described in this slide. So this all began in, 2002, really coming up with the basic requirements of like who's responsible, what kind of framework are we gonna operate in, and that kind of stuff. Then there was a multi-year activity to try to find a site. So what NWMO did is they said, we want to find a site, we want a host community that is willing and able to host this deep geological repository, and say, it's almost like they put it out for bid, right? Like a request for proposals. They said, please communities, think about this, whether you're willing to do that, and here are some other benefits that could happen to your community, economic benefits by having all these jobs and stuff like that to your communities. So 22 different communities across Canada said, yes, we're willing to host a site. Then that was down selected eventually to 2, and then right before Christmas, there was 1 site that was selected. So that was right before Christmas. Now here in 2025, if I'm getting the right slide, yeah. The next stage is starting to get ready for construction. So that's where the license process described on the last slide maybe makes a little more sense. License to prepare site, license to construct, license to operate. And so it looks like, if everything works according to their plan, the removal of spent fuel from different locations across Canada to this DGR will be in the 2040s, just to give an idea of the time frame. The basic idea with the design is what's called a multi-barrier system. So for the nuclear people in the group, you may remember me talking, hopefully you remember, defense in depth. So the basic idea with defense in depth is that people aren't perfect, engineering designs aren't perfect, things can go wrong. So the idea with the defense in depth is to have multiple independent mechanisms to ensure safety. So if you think about it like, you may have heard like belt and suspenders kind of approach to keep your pants on, right? So you can have a belt, like most of us are probably wearing a belt. Imagine wearing a belt and suspenders. In this approach, there's 5 different mechanisms, which is consistent with other nuclear engineering designs, such as nuclear power generating stations. In this case, the first one is the fuel itself. So what we really want to prevent is the release of these radionuclides. So the fuel itself, the hard, dense ceramic, is the first mechanism to prevent that release. The second one is the bundle itself there, that you guys all had passed around the room. So you have the zirconium alloy, what's called sheathing, that provides a metal barrier for that release. The third is what's called a used fuel container, or UFC, which I'll describe in another slide here. It's basically a large steel vessel that's intended to provide a pressure boundary. Number 4 is a bentonite backup, like a backfill. The main purpose of bentonite, well, does anyone have cats in the room? Few cats? So kitty litter, right? So one of the main ingredients to kitty litter is bentonite clay. It's just like, your cat does its business in the kitty litter box, and that bentonite just soaks it up, right? That's this, basically. No Purina, or I don't know what brand. So this bentonite clay is really intended to soak up all the water if there is any water ingress. So the idea there is that if there was any water, it'd be soaked right up by this bentonite so that it prevents another barrier from that water potentially corroding the used fuel container. Last one is the geological geosphere that surrounds it. So the geology, the location of it, that itself provides this final barrier for radiological release. So you can see like the schematic like on the slide and how that's kind of arranged. To give you a bit of an idea of how this room looks, NWMO has like a demonstration room that you can actually go. It's in Oakville. They have tours, you can check it out. It's called a placement room. So you can go inside and get a sense of like what this looks like. They also have samples of this used fuel container, also bentonite clay. I think the Canadian Nuclear Society arranged a tour of that not too long ago. So for students, you can maybe keep your eyes open and check it out for yourself. There's me like with a bunch of my students a few years ago checking it out. The used fuel container is about 2.5 meters long and a little over 0.5 meter in diameter. Looks like a giant pill. The purpose of this is to provide mainly like a pressure boundary, like a mechanical rigidity surrounding the fuel itself. The thickness is about 2 inches thick and has a copper layer around it. So the used fuel bundles are then going to be relocated into this container, and I'll explain a little bit more about how that happens in subsequent slides. And you can see a picture of one of these used fuel containers in this like bentonite clay box. One thing that's worth noting, part of the design basis to determine like the thickness and the structural rigidity of these things, one of the accident scenarios that's being considered is thinking on a geological time frame, the possibility of what do they call it, like an ice age, and the possibility of having 3 kilometers of ice on top of the geosphere here. So that 3 kilometers of ice would obviously add quite a bit to the stress that would be experienced within one of these placement rooms. So one of these is designed for that purpose. So you can see over here how these different used fuel containers are located. Inside of these placement rooms, they'd be staggered. As you go inside, you would have like these bentonite clay holders that would hold them in place. And then the used fuel containers would be staggered going across them. And then the idea is when you have a room that is filled, then you'd backfill it with more bentonite clay and then concrete eventually to close it out. A little more complicated than that. There's like an extended monitoring period that monitor for the potential for any radiological release. Question about where is it located? So like I said, right before Christmas, just a quick question. How am I doing for time? 12 minutes? Okay, so it's all right. Okay, so the site was located right before Christmas, and it's called the Rebel site. It's near the Wabigoon Lake Ojibwe Nation, near Ignis, northwestern Ontario, located about 260 kilometers northwest of Lake Superior. So 260 kilometers, I mean, that's like almost Kingston, I guess. Probably somewhere like in that kind of space here if you want to get some perspective. This is what it looks like in one of those locations. Looks like Northern Ontario. If anyone's been there, it looks very similar. So in this location, there's a number of things that were determined, as part of the design requirements for the site selection process. One of them is seismic activity. So the government of Canada measures seismic activity, I think since 1980, into various parts across Canada. That includes not only the location, but also the magnitude of any types of earthquakes. Generally, we don't have a lot of earthquakes here in Canada. Compared to other places around the world, we definitely still do get them. A lot of them are so minor that we normally don't feel them, but they're still there, and they are measured. There have been a few instances of some larger ones. I remember, 5-10 years ago, there was I think a category 4 or 5 in Ottawa. So this is definitely something to be thinking about. And so this map shows the location and frequency and different magnitudes of different earthquakes in the Ontario region. This particular site, I guess you can kind of see it here. We're looking northwest of Lake Superior, so it's kind of in this area here. So not a whole lot going on in that region. That's one of the motivating factors for the selection of this particular site. Other ones include, I'm not a geologist, I'm more of an engineer, but there's, it's part of the Canadian Shield, which is geologically quite stable. There's several concerns to be thinking about with the potential safety cases of spent fuel. You talk about the potential for like an ice age. There's potential of water ingress. And the reason why that's a concern is that you may have corrosion of your used fuel container. And if that corrosion continues over a number of years, decades, centuries, that's something you definitely want to be thinking about. And even if that does fail, what would happen? So for example, if you have water ingress that breaches the used fuel container, how does that water then interact with the fuel itself? Now, this is a really complicated subject. I told you there'd be some chemistry. So in this case here, it's incredibly complicated, partially because the chemistry of the fuel is so complicated. You also have the chemistry of groundwater in that region. So previous studies of irradiated fuel in contact with water very much depends on the oxidizing or reducing conditions of that aqueous environment. Generally, the kinetics is significantly higher in oxidizing environments, not entirely surprising. Reducing environments are a lot more favorable for fission product retention. So one of the other reasons why this site was located is that its tendency for reducing conditions of potential groundwater. Okay, so on top of this repository is plans of having what are called surface facilities. So these surface facilities would include things like receiving the spent fuel that would be coming from the different nuclear generating stations and whatever sources. There's some handling that would be required, transferring from one unit to another, getting it into a used fuel container, welding it shut, monitoring, security, all that kind of stuff. This is the intent of having it up onto the site. And you can see the main shaft located here to relocate the used fuel containers down below to the repository. Question that often comes up also is how do you transfer it? How do you bring it over different sites? In Canada, we have a licensing process for used fuel transportation packages. A picture of that is shown over here. This is a little bit different than the dry cask that I showed a bit earlier on. It's basically just a lot smaller and more amenable to be able to put it on a truck. The big problem with those used fuel dry cask or used fuel containers I showed earlier on, the big giant ones, 60 tons empty, 70 tons full. If you were to put that onto a truck, you have to put on what are called impact limiters that brings it up over 100 tons, and it's enormous. So big, you can't really practically put on a truck. Rail is one thing, but there's all sorts of transportation problems with that. So the current plan, at least what it's leaning towards, no official decisions have been made yet, because again, it's part of the licensing process, is to use this used fuel transportation package shown here. So this package includes not only shielding to prevent, to provide shielding for that radiation, but also, if there's something goes wrong during the transport of that fuel from the site to the DGR receiving facility. Common question I've heard is like, well, what if something, there's an accident? There's three primary accident scenarios that are considered for the transport of used nuclear fuel. Impact, so it means like if you have a truck that has a head-on collision, for example, with another truck, or you have a fire, like you have vehicle collision, gas fire, that's not good. And the third one is water immersion. So for example, a truck drives off a bridge and ends up in Lake Superior, for example, or Lake Erie, whatever it might be. What's the problem there? Because obviously you wouldn't want those radionuclides coming out anyways. I used to work at Chalk River up in Northern Ontario. We had this facility, a drop test facility. It was like 9 meters. This is like a picture of it. So what would happen is that you take one of these transport packages, raise it up to about 9 meters, and do a series of tests. These tests include like drop tests where you're flat on. So if this is the ground, here's the container flat on or at a corner. And we also did one, well, not me, but other people at Chuck River. It was like a puncture test. Basically, imagine like you had like a roofing nail on the ground and you stepped on it with your foot. The reason why it's important is because that's a high stress concentrator, right? So those are the kind of tests that are done for drop tests. And you can see right here that it's still in good condition, relatively speaking. It survived, no radionuclides released. The picture you see on the right is the exact same container. It's an important part to note. So after that drop test of 9 meters onto hard concrete, then it was lit on fire. I can't remember the specifics of it, probably just like a big gasoline or kerosene fire, but ran for about an hour or so. So it worked out pretty good. The other one is impact tests. These ones I think were done at Sandia National Labs with the train. Sandia has some pretty fantastic testing facilities. So what they do there is they have an unmanned train that can be remotely operated, and they'll do like an impact test. In this case here, this is a 160 kilometer test. The idea there is that with the big limiting factors are really 2 trucks hitting each other, where like the truck that would actually be transported would not be running typically at 100 kilometers per hour. The concern is basically on the Trans-Canada Highway where you're limited to 80 kilometers an hour. 80 plus 80 is 160. So here we got a train moving at 160 kilometers per hour with a direct collision, and there it is right there, and worked out all right. Just wanted to give you a sample of what's done in some of the testing. Also for any of the engineering students, you know, it'd be a fun thing to do for your job. Another question is like, what do you do? Like, who's gonna pay for all this? The way that Canada works is by law, the polluter pays. So what that means is that whoever produces the waste, every year they have to put money into a trust fund. So what that means is that every year the amount of money that is put into that trust fund is proportional to both the amount of spent nuclear fuel that is generated and the anticipated costs of the deep geological repository. As it stands as of 2023, that amount is that's $5 billion. So $5 billion is in the bank right now to pay for this. I don't know what the actual costs that are anticipated for this site, but in Finland, who are further along with this process, they've estimated 1.5 billion euros, which is about 2 billion Canadian dollars. A little bit of apples and oranges, because they may, you know, probably have a different inventory that we do, but gives you kind of the you know, order of magnitude of you know, few billion dollars. Another question I'm often asked is like, what are other countries doing? So first thing, before getting into how different countries manage their waste, it's worth acknowledging, you know, what kind of inventory, what kind of waste do those other countries have? Again, I'm focusing on high level waste, not the lower stuff. Here I have on the figure on the left, Latin America, North America, Far East, Western Europe, Eastern Europe, etc. Clearly from this plot, North America and Western Europe are the big guys producing a lot of waste. And you can also see that there's different forms of that waste. The Western Europe front, you may notice that there's a checkered pattern that says reprocessed. There is a technical means for essentially recycling used fuel. There's both technical, economic, and socio-political vectors on that that makes it, you know, very different depending on which country you're in, but just acknowledging that that process does exist. The projections to date is shown on the right, all the way up to 2050. I'm expecting that that's going to be even higher now, given some recent announcements here in Canada. But what's looking like the amount of waste is going to be is expected to be increasing quite a bit in the coming years. The countries that are furthest along with this process are Finland and Sweden. They're basing on what's called the KBS3 method. Sounds kind of random, but that's basically an acronym of the company that came up with this, and 3 is being the third iteration of their design. In that method, it's very similar to what's been adopted here, and for good reason. In their case, their fuel looks very different than that fuel bundle that we passed around earlier. The fuel is quite different in a few ways, but also very similar in other ways. One of the big differences is the size. So each one of their fuel assemblies, instead of being about 0.5 meter, they're about 3-4 meters high. And so what that also means is if you have more of that fuel, the radioactivity is proportionally much higher as well. So what they plan on doing, similar to us, put it into a carbon steel like pressure vessel and then coat the outside with copper. The copper layer is there to prevent corrosion. And then when they're out of sight, imagine like we had those placement rooms that I showed you earlier in the Canadian design. In the Western European design, they have like a tunnel kind of going across. They drill in various holes into the geological formation, and then they'll drop in their canisters in that way, and then backfill with bentonite. So a little different, a little similar as well. I think I'm doing okay for time, right? Excellent. So to summarize, my intent for this is to be, technical and provide you like at least technical information about what this whole like spent fuel is about. There's the dangers associated with them, but also the engineering approaches to mitigate those hazards. One of the main themes you may notice is that there's some international consensus in the approach. There's a lot of coordination from one country to the next on how to best handle these situations in terms of engineering design. There's a multi-barrier approach that's typically used in these different designs. So that's kind of the idea. If you're interested, again, I'm going to make these slides available after the lecture. I put in some additional materials here in case if you're like really keen or like you're having trouble sleeping at night. You look like you don't need the report anymore. You're good to go. Big yawn. So we got some great reports here, some technical reports. If you're really keen on getting a sense of that, we have some international reports from the International Atomic Energy Agency, Natural Resources Canada. If you're really keen on like a lot of that more technical stuff, at least in the chemistry of the fuel and things like that, there's a book chapter here just on the fuel chemistry, and there's more of an engineering approach from another book chapter shown here. As people here at the McMaster community, you have access to both for free. You get it through the library. There's a really neat YouTube spent fuel pool at the Bruce Nuclear Generating Station, and also how they handle these dry storage casks. Also, if you're not aware, here at McMaster, you can also do a tour of the reactor. So if you want to do a tour, you can just click on that link and schedule something if that's something you want to do. I know Ramis did, hopefully. Did you do it already? Yeah. Okay. Well, enjoy in February. Okay, with that, happy to take any questions. Also, if you don't mind, if I get those pellets back, because I'll use those in future classes. Please and thank you. Yes?
So it all seems to be in consideration the CANDU design. Also, whether it be CANDU 6 or pretty sure it can be similar to a story. However, I did hear that Ontario were introducing a different type of reactor, the EWRX 300s from G. So definitely a different design and they're using low enriched instead of sample. So are you aware of any considerations made at the repositories waste from the EWRX 300s that you're seeing?
Yeah, sure. Let me take a step even further back. So here in Canada, there have been additional different reactor designs, not just the X300, which is somewhat similar in design to CANDU in some ways. The other reactor designs are much, much more different, where the fuel forms are completely different. So in both the CANDU and this X300 design, the fuel is uranium dioxide, got a whole bunch of fission products in there, you got zirconium alloy cladding, that's similar. The other ones include like salts, fluoride and chloride salts, totally different. Another one's called trizo-fuel, where you end up having a whole bunch of layers inside of it. There was another one that was considered in New Brunswick, that's a metallic fuel, totally different. What's worth acknowledging is that they're all very different, and it doesn't make sense to respond to all those reactor designs until there's some guarantee that they're actually going to be built, right? It's business. If like the business doesn't proceed, then there's no point. So the one you mentioned, the X300, looks like it's proceeding. Just finished the last stage of the license to construct application. There aren't any public available reports yet. about how this DGR may change in that regard. There's some discussions about the fact that the used fuel container will likely, will have to change. However, many of the other components will probably be the same. Now, for me, I'm just going to speculate a bit. My guess is that, an educated guess, is that what they'll do is they'll probably have a second used fuel container, similar to what we see in Finland and Sweden. The ones in Sweden and Finland are designed for this other type of fuel. That's my guess, but speculating on that part. Yeah. Yes? That waste heat is very low. It's too low really to make anything useful of it. Yep. Yes?
What's going on?
Yes. So I got an hour today. So what you got to do is you got to take some of my classes, and we'll talk about these in detail. Give it a plug. So I got some of the students that already taken some of the courses. You guys got to take some more nuclear courses. We'll go into more detail. To answer your question, yes, there is some monitoring in place as part of their larger phase management program. So what that means is that when the used fuel is initially put in underground, the intent is for that to be monitored for several decades afterwards. I keep using this term adaptive phase management, and what it really means is that the intent is to be somewhat flexible in their approach at different phases, like different milestones of the overall project, so that they're not trying, again, I'm not representing Nuclear Waste Management Organization, they're not paying me for this, but the intent there is that, you know, as more data becomes available or different information from different stakeholders come about, that they can change their design. As stands right now, their intent is that once all the fuel is put in, they're going to monitor for several decades. And then after that next checkpoint, they either wait even longer to continue monitoring or fill it up. Filling it up means backfill with bentonite clay, concrete it up, and close the site. Yes.
Start off with radioactive dioxide, you end up with metal oxides stuff. And I'm just curious whether or not that mixture is what I would call the thermodynamically best oxidized system. You talk about the subtleties of not the water oxidizing. Surely you want to go to a system that is as oxidized as it's going to be, so that it's kind of not going to want to react further. Who wants to do chemistry on this metal soup? I'm just curious, would that make sense to actually oxidize whatever that goop is to its most stable form? Or is it because it's dynamic forever that doesn't make sense anymore?
First of all, my students do that thermodynamic analysis, so there is some interest. But yeah, so what we find is that the most stable form is the uranium dioxide itself. ODM. So all of the other metals, all the other fission products, for the most part, they're dissolved within that fluoride matrix. So they're all within the grains of the uranium dioxide, with the exception of some of the gases, so the gases and volatiles. Those ones don't really oxidize. So like iodine, for example, xenon, krypton, they don't really oxidize. The other ones do, and they form very stable oxides within that fluoride matrix. Yes?
It's actually related somewhat to my question. But I haven't that actually incorporates that fuel into the process like glass images. I believe French are doing this.
So the conversion to a glassy matrix is done for very different reasons. That is not really applicable to Canada. One of the reasons why the French are looking at converting part of their high-level waste, not spent fuel, to glass is because they also do this other process with reprocessing. So the conversion to glass is mainly done for that purpose. That's not applicable really to the Canadian landscape. Petru?
There a specific reason that they were selected to be most large bodies of water? Do they have roles in some sort of maintenance of the BIMR, or am I just?
The site's 260 kilometers from Lake Superior. So like that's from like Hamilton roughly to Kingston. That's pretty far.
The transfer of reality of thorium reactor, they suppose much more, much cleaner in the byproduct.
Okay. So this is out scope of this presentation, but I can talk about that. So yeah, there's been some interest in some thorium type of reactors. One of the important things to understand with thorium is that it's not fissile. It's fertile, which means that you need to marry it with something that is fissile, like uranium. And the neutrons that come off of that uranium can then interact with thorium, converting that thorium to uranium, and that burns. So one of the important things to understand with that is that you need to marry the two together. So if the intent is, let's say, to go to a thorium reactor, and there are some like minor benefits, I like to say that they're minor, they're not like substantial, minor benefits, you still have all of the other challenges you have with uranium. So the main benefit really of having a thorium type of fuel cycle is that there's about 3 to 4 times as much thorium as there's uranium. So if you were to couple uranium with thorium in an alternate fuel cycle, what that really does is gives you more resources to work with. Hope that answers your question.
Okay,